Okay, it did say it connected. So all right, so hello, Kyle. Hello, Todd. I am still not sure if we are on air or not. So I will know in a few seconds, and we can officially get started with this. And yes, we are on air, and I can see the screens, and everything is working. So this is a little bit. Hello, everyone. We're gonna give it a little bit of time so that everybody joins the stream. But this is a little bit a special, as you can see. This is a special broadcast from Electro Impact. This is it's so much fun. What's gonna happen? You are going to hear a lot of background noise, and that is okay because this is live streaming from a facility. Awaiting for more folks to join in and tune in to us. I'm going to start by saying hello to Kyle and Todd. Kyle, I'm going to start with you. Can you go ahead and introduce yourself, please?
Hi, I'm Kyle Jeffries. I'm a mechanical engineer here at Electro Impact. I'm one of the leads in the AFP Composites Automation group, and I've been with the company since the mid-90s. And yeah, go ahead.
That's awesome. And you're one of my friends, Kyle. So this is it's good to know you, and I just love the background. I'm gonna go ahead and try to maximize the screen in the solo layout so that people can see a little bit the amazing background that you guys have. This is a real AFP machine, and we're gonna get to talk, and you're gonna be introducing it in a little bit of time. Todd, how are you doing?
Great, Rami. Thanks for having me. My name is Todd, as Rami said, and I'm the director of the fiber placement group here at Electro Impact. And really pleased to have an opportunity to share what we're doing here in our development center.
All right, that is awesome. Thank you so much, Todd. You do introduce yourself as the director of AFP as well, so this is awesome. So for everyone listening to us on LinkedIn, I know that you're gonna hear some background noise, and that is okay because we're having a live stream and it's from a facility. So just go through that a little bit with us. So Todd and Kyle, you guys have a presentation. We're gonna power through. This is really more of a discussion we're going to have with each other. And if I understand correctly, we're gonna try to cover 4 elements. So what Electro Impact is capable of doing, the motion platforms, Electro Impact technologies, and the Electro Impact processes. So we're going to be powering through this, and we have some videos as well to play every so often. So let's go ahead and start with Electro Impact capabilities. Who wants to talk about that? Is it you, Todd, or is it Kyle? All right, go ahead, Todd. Tell us, what are we seeing in here?
Okay, so what you're looking at here is the one of the machines in the Electro Impact Developmental Composite Center. It's a huge machine, very large envelope. Matt, go to the next slide, or if you could, Rami, go to the next slide. Machine that you just saw a picture of, I'm sitting in that cell right now. You can see that we have a huge envelope machine here capable of building, that happens to be the better part of a 777X wing spar in here. We've built 777X wing skins in here. We've built a bunch of neat parts for Airbus in here. So we get to do a lot of work in here. If you have a large part that you need to see or if you need to develop a process for some sort of large part, you want to see if AFP is the right solution, whether it be thermoset, thermoplastic, or dry fiber. We can handle all those materials here and stuff.
All right, this is awesome. So how big are we talking? So I see on the screen there is, we're talking about 84 inches travel in Z, almost 300 in Y. And I don't know if I can see it, but how far is it along X? Can you travel? Is
Yeah,
it like,
it's about 80 feet in X. So
oh, wow.
it's a big envelope. And the head can hit all 5 sides of a part. So there's no, the swivel head can hit, if you imagine a 5-sided part, we can lay AFP on all 5 sides. So.
All right, that's awesome. And this configuration, you said principally you guys are doing this for which part? I heard it's the wings.
Yeah, so this machine is actually, an exact copy of this machine is in Boeing's Composite Wing Center for the 777X, and it manufactures the wing skins for the 777X there,
All
as
right.
well as wing spars, so both parts.
All right, awesome. So let's move on to the next chart. So what is it that we're seeing in here?
So now, can you hear me okay?
I can hear you perfectly, Kyle.
Okay. So we have the big demo gantry that Todd just presented there, and we also have a couple of robot assets that R&D and are in the same facility. So we have a large temperature controlled building here that houses all of the projects that we build for customers, the machinery, the robots, the gantries, and it also houses the demo gantry you just saw and the robot behind me, and all of the robots that we use for R&D. So the assets, the end effectors that we use on the demo gantry are transferable between any of these machines. They're all modular and quick change. So we can take a process or an end effector and bounce it to whatever asset we have available to do testing at the time. And we do material development, process development, part trials, all the things that Todd named with these things. We have some videos if Matt wants to throw one up of the robots in motion and the demo gantry building some parts here. Let's see if we can fire one up.
All right, awesome. So go ahead, Todd.
Yeah, so Matt, you should be sharing Matt's video here of our building up the EA Developmental Composite Center. You can see the demo machine on the left, and you can see a series of robots on the right. Some of those robots are production robots, and they're actually being shipped, already shipped to customers. The last 2 robots are actually our robots. We keep them here for all sorts of development work. We have our own agenda, and then we also go on whatever agenda or a college or whoever. So we do all types of process development. We have that tool fuzzied out so you can't see it because it's some super secret thing that we were working on for somebody.
Yeah, I totally understand. It's when you. I wanted to say to the people watching us, and there's plenty of people saying hi and hello, and a big hi to them. I wanted to say that the blurry picture that you see is actually intentionally blurred, and it's not because of the streaming. All right, awesome. So what does RCADE stands for, like in your terminology? So I can try to guess if you want. R for research, development. So go ahead. What is RCAD for?
It is a research composites automated development equipment.
Hey,
It's not a great acronym, but you got to make a cute name. So we got the cute name.
Arcade Hub. All right, cool.
Yep.
I agree with that. It is kind of fun, the world of AFP.
Yep.
All right, so what is it that we want to talk about in here? Is this some of your specific material trials?
So that's a great overview of the arcade cell. That's the arcade cell in actuality. So we use these 6-axis KUKA robot arms, and we accuratize them. We have a patent for accurate robot technology where we put optical scales on each of the joints to give actual position feedback. And we don't use the KUKA controller for motion. We use a Siemens 840D. We feed the feedback into it. We get a really nice, accurate robot. You can see it's on a 7th axis, a linear slide there on the floor, the blue piece. So we for customers. We do these with and without the 7th axis, depending on the part family you try to reach, basically your working volume of the system. The 7th axis obviously gives you some flexibility in working volume. We also pair them with rotators, so vertical rotator, horizontal rotator, and even parts as large as 20-foot diameter, 50 feet long. We have done layups for production with these AFP robots.
All right, so this is the arcade. Yeah,
that's arcade.
Yes. So is this like your own little makeshift table to try the layup on, or?
Yeah, that piece there is just a piece of test tooling, and so that's flat layups. So we might pull coupons off of there doing process trials with a material vendor like a carbon company. They'll come in and do trials with us to help develop the next generation of composite materials for prepregs or dry fiber. And so you end up in those situations, you start with a lot of flat panel work, and we'll use a simple tool like that. And then at the end of that previous video, you saw the blurred out tool, and that's where we get into the more complex geometries and use full contour tooling to do trial part builds.
I actually wanted to ask you a question. So did I see correctly in the video that you played, there was a tool, it was like mounted on a mandrel, but it was not actual, it was like shifted and it was like rotating around it. Did I see that right, or
you saw it right?
Okay, I saw it right.
We'll call that a party trick. So anybody can lay up on a round tool that's concentric to the spinning axis to make sure that we had all of our kinematics correct for more complex spinning geometries. We canted a pipe on the tool so that we could test and demonstrate our kinematic control.
All right, this is awesome. I see Matt has another video ready for us. Should I go ahead and try to see?
Yeah.
All right, so what is it that we're seeing on this one, Todd?
Okay, I've jumped ahead to the robot video for Kyle so you can continue.
Oh, okay,
so
yeah, this one.
There you can see the party trick in a little more detail. And again, that's just a demonstration piece to work out our tricks. This is an actual customer layup where we're doing layups over core. And you can see here that the core height is fairly significant and the core ramps are pretty steep. So it's a very challenging layup. It's very difficult to get all of the material down into the concavities without bridging, and to have accurate control of your compaction force so you don't crush the core. This part, you got a spar shape where you've got a 3-sided part. So there's your small vertical rotator. Again, the trickiest parts of a spar are getting really precise kinematic control, so you know precisely where the tool point is as it goes over the radii, and you get really good toe placement, no laps, no gaps.
So for those of you who are just joining us, and I see that the numbers are going through the roof, this is we're having today a special live presentation from Electro Impact in Washington State, and we have Todd Rudberg. Todd is the director of AFP, and we have Kyle Jeffries, one of the mechanical engineers, the pioneers working on AFP since the 90s. We're having a lot of different demonstrations as well. So this is awesome. All right, cool. So moving on within the charts, what is it that you want to focus on these charts? We're seeing the head up close and personal. And so tell us a little bit about the development of this head.
Yeah, so this is another view of, this is the arcade cell again, but you can see a close-up of the end effector there. So Todd and I have been working in this Composites Automation here together since the group started at Electro Impact. So we've seen this technology come from its infancy to being really mature for production and R&D environments, and we definitely have an eye for the future. This product, the 16-toe head on the left, was designed with kind of a clean sheet look at how to handle the sticky black stuff, but increase the deposition rates, obviously, and also increase reliability of the process. And so the whole head was laid out with the idea of a modular head that disconnects from the machine with a robotic tool changer, and it gives you process flexibility, and it also allows you to remove the process end effector from the motion platform when you need to replenish the spools or do periodic cleanings. And so it was kind of a revolutionary concept at the time, and part of the thing that came out of it was a very short, simple tow path, in contrast to AFP machines of the day. It turned out that short, simple tow path, while allowing us to build this small modular shape, also drove up the reliability by big factors. It's sticky black stuff. You want to touch it as few times as you can, and get it on the part as quickly as you can.
You don't even want to try to touch it in some instances.
Yep. The ideal is not to touch it. So we got as close to that as possible.
All right. So let's see. So this is a little bit what you're talking about is this modular process heads, the capacity
Correct.
to easily inspect them, easily correct them, easily replenish material, easily clean up if you want to, and reduce as much as possible the downtime. So let's talk a little bit about this. In a recent presentation I made, I did. So my numbers come from academia, so from estimation, that the estimated downtime for inspection, of course, it's not a problem, but inspection is part of the process. For inspection and repairs of the machine goes more than 50% of the time. Is this something that you've observed as well, Todd? Is this something that you can talk to us a little bit about?
Yeah, I'm really glad you brought that up. That brings up, if you go to the next slide, inspection stuff on there. But basically, we've started the development of a new AFP philosophy. When we started, the world was on AFP, what I would call 1.0, and that would be your Cincinnati machines, Vipers, generally doing layups and kind of struggling their way through, all the way to where we're at now, where I would say we're at AFP 4.0. And AFP 4.0, we've kind of looked at the whole process, including inspection, and all the other time items that occurred in what we call the ply-by-ply cycle. So we're currently developing that technology now. And if you go to the next slide, I think we should have some video of, or we should have some inspection related stuff. Well, actually, this is a great slide to look at. So here's where we're at on AFP 4.0. This is one of the test parts we're making. It's a very challenging part. It's got lots of short toes, lots of little tiny gaps, and a lot of ways to trip up the AFP process. So we're very good at doing that layup, but we're also very good at inspecting it. We want to make sure that the ply fill meets the criteria that the designer who drew the ply boundary was there. So our equipment will now automatically determine if you meet those ply fill criteria, and it does it real time. If we go to the next slide, I'm not sure where we're at on the next slide. Okay. All right, let's go ahead and show the AFP 4.0 video, Matt. So Matt's going to play a video here. And basically what you described is the problem. In 3.0, you're getting really low runtime. Hopefully in 4.0, and actually we're demonstrating in 4.0, extremely high runtime percentage. And the way that helps you is we're not running the machines any faster. We're just running them more often. So you really get a lot more utilization. The goal with AFP 4.0 is to deliver anywhere from 3 to 6 times the amount of throughput in an AFP cell that you would typically get in today's world of the ply-by-ply cycle. So you're seeing here our AFP machine in the demo cell performing the layup. And I'm just going to let this play a little bit. I'll talk it a bit. The machine is laying up at 3,000 inches per minute. So every add cut, every event that occurs.
Oh, wow.
Extremely fast. And then when the machine finishes apply, instead of stopping and somebody coming out and touching it, since the inspection process and is done automatically and the ply fill is assured, we continue on to the next layer without any type of manual inspection. So we've completely automated the inspection process, and we demonstrate it daily here. We also do live streams once in a while when we're feeling pretty confident. We do a live stream. We say, oh, we'd like to fix these 5 things. We go work on those 5 things, and then we'll go do the live stream again. So we'll, if we had an email list, we'll send out to the email list to everybody we'd like to see, invite to the live stream. And basically all you're going to see is an AFP machine running 100% full out, 3,000 inches per minute for about an hour. It's about how long it takes to empty the head. And every ply will be inspected. We won't drop any toes, hopefully, during that. Typically, we don't. There's equivalent of over 10,000 toes in that part. We talk about mean strips between failure. Our goal for AFP 4.0 is to have a mean strips between failure in the 100,000 range. And to put that in perspective, Section 41 of the 787 has about 180,000 strips of toe in it. So,
oh, wow.
Talking about maybe not dropping any toes for the entire part of an entire twin aisle fuselage. We've used this downtime that we've had for the COVID scare to really press hard on this. We weren't able to go into some of our customers' factories, but because we're transportation related, we're considered essential business, and we've just carried on working very hard developing our reliability mechanisms. How do we reset the head to 0 so it will always work? How do we do this real-time inspection? And honestly, we've been working on it for a couple of years, but very intensely the last couple of months. And this video is a result of that.
I can totally imagine that, being confined into doing less travel and because of the situation that's happening, I'm gonna, how to say it, I'm wrapping up so many documents that were so long due that I was telling everyone, you know what, hey, I will give you that next week. And suddenly now I'm delivering on those documents because I can go to my lab as well.
Yeah, in a way, it is an opportunity. Of course, you have to try to find the silver lining in every dark cloud, and that's kind of what we did. We said, well, our plate's clear for the next couple months. Let's really dig in on this. And so,
and we always have to do that. All right. So let's talk a little bit about this, Kyle. So what is it that we're seeing? Oh, I had a question before we move forward. Was that demonstration that you just showed us, Todd? Was this a blackbird? What was the shape?
Oh, the blackbird. It's the SR-7.
It's a blackbird. All right, cool. I was like, it looked like a blackbird, but
yeah. Can you go back one slide?
Yes, I can. This one.
Okay. So this is what I'm going to skip 2.0 and 3.0, but basically this is what embodies AFP 1.0. This is very old equipment. Probably designed in the 80s, 90s time frame. I don't know when this particular piece was built. But you can see it features a creel house, a refrigerated toe way in the back, and then a 30-plus foot or 10-meter tow path out to the tool point. And that was great for the time, but it had to move forward. And then where we're at now is what I call AFP 4.0. If you go to the next slide, you can see an example of the newer machinery that has the creel located out on the process end. The heads are modular. They come off of the motion platform. They're motion platform agnostic. You can see that on the left picture, you have a robot holding an AFP 8-toe AFP head, and on the right, you have a machine holding an 8-toe AFP head. So, like I said, totally motion platform agnostic, and that robot there can easily hit the same envelope as that older Viper equipment. So
question. Industry wants to have more and more productivity. Having a 8-toe placement head seems a little bit. I understand, like it can go into more location, more concave locations, but this looks like a pressure vessel or something of the kind. I don't know what that is from this view, or this can be those parts 47, 48. I don't know what it is from this viewpoint, but why would I be interested in having a 8-toe placement head?
I can answer that. So yeah, it's a great question, and you're kind of hitting it on the head there. So in the right-hand view, you can see an 8-toe head that's in an obvious concave mold, and so that's an obvious need for just a smaller end effector that goes inside a concavity. The left-hand picture of the pressure vessel build, the trick there was they had tooling where they wanted to minimize the diameter of the rotating shaft, but lay up really, really, really close to it. So in this case, they wrap all the way, they kind of wrap the end of the pressure vessel and come really close to the support for the tooling for the rotator. So they needed a smaller diameter head.
Is this something that Matt wanted to try to show at this time? So I have one video from Matt. Is this a video that he wanted to play?
Yeah, we could play that.
Yeah.
I don't know. Is this the process one? So this is
more
process related. So here we're showing the layup of dry fiber with our equipment. This is one of the developmental things that we can do here. This was done on the demo cell. That's a spar part. It's not a Boeing one, but it's still a spar, legit part. And you can see that we're able to lay dry fiber very effectively with our process head. It took us a while to get there, of course, and we had to involve bringing in lasers. We do integrated lasers, and we do third-party COTS laser systems that keep it strap on to the head. In that video there, you saw the third-party COTS one, sort of the strap-on, but equally effective to our integrated one. Just restricts the machine motion because of the umbilical. But we also have fully integrated one into our AFP head.
So I have a question. What is this heating mechanism I see? Is this this is not IR?
Yeah,
and this is not
IR laser. It is an IR laser. It's made by Laserline. It's the most common, I would say, the most common laser used in fiber placement today. If you walk around, you'll see Laserline systems melting composites together all over the place. We also have our own proprietary integrated IR laser system that we're in the middle of patenting, and I'm not really going to go into the super deep details, but it is very effective, and it's 100% integrated into the modular head.
All right, awesome. I'm looking forward to hear more about that. So I think in here, this is the point you were talking about, Kyle, before for the pressure vessel, that the robot volume reach, the envelope for accessibility is quite substantial.
Yeah, in this case, what we're trying to show is it's similar to the point you're making, but the tan embodiment in the background there is the basic reach of, like a Viper type of AFP system. So back to the AFP 1.0 style. And overlaid is one of our robotic arms with a head, and it's just showing that green volume is where the robot can reach. And the robot is a very inexpensive motion platform. So at a fraction of the price, you can get something that dwarfs the reach of those old systems, and also gives you a lot of flexibility. And one thing that we do a lot with these systems out in the field, and the green volume represents it, is we can work on either side of the robot bed. And so we can be laying up on a part on the left side of this screen here, as shown, and we can have somebody rolling in a tool on the right-hand side and prepping for a layup after the left side finishes. And so we've done that a lot of times out in the field where we have two separate safety interlocked work zones. So we can bounce between them and kind of pendulum the system again to maximize the utilization of the system.
All right. So what is Ripit? Is this what enabled 4.0, Todd?
Yeah, it's one of the elements of 4.0. There's probably 4 or 5 different technologies that lend itself to AFP 4.0. I'm going to highlight this one, Ripit. It's a cool name, stands for real-time in-process inspection technology. And what it is really is real-time ply fill assurance. So the designer said, I want this shape filled. He makes a program. What Ripit does is make sure that we adhere to that ply fill by ensuring that the toe ends are in place. It ensures that the lap gaps are between each of the toe interfaces is within a specification. And we're also doing FOD now. So we've got pretty much all the aspects of ply fill handled with this, and it takes about 5 seconds after even the most complicated ply is completed for the inspection to be done, and we're able to go on to the next ply.
So in some sense, Ripit enables you not to rip the toe at the end to replace it.
That's right. We are driving, like, with every bit of energy we have to get rid of the need to touch the part with human hands. And we've made huge progress even in the last 3 months.
That's awesome to hear.
Now, this is just real quick. I'll cover this slide, and then we'll be done with inspection. This inspection system isn't just a pipe dream. This inspection system, Boeing cannot build a 777X wing skin without this inspection system running. So this is Boeing certified legit stuff. You're actually looking at a screenshot from a part that's been inspected in the field at Boeing.
So I mean, is my understanding correct that you're officially skipping a human inspection using the system?
We are not doing that. We expect that our customers will demand that in the very next go round. We are
all right. All right. So what are we talking about here? I see some heating mechanisms. I see some ultrasonic knives. So what is the topic du jour?
Okay, so there's a couple things here. Todd's mentioned, so we've been talking about where a lot of our R&D goes, and very recent R&D, and that's been the kind of the highlight of that AFP 4.0 discussion. This kind of highlights a few R&D over the past couple of years, and so, you know, alternative materials. Matt has some videos that he can play whenever he's ready, and I'll just keep talking. But the three probably key pieces. This video is showing a thermoplastic layup, and so we kind of delved into the thermoplastics over the last 2 years, and now we're, you know, among one of the industry leaders in thermoplastic processing. And everybody knows some of the keys to thermoplastic processing is a high intensity heat source. And so we've experimented with several different high intensity heat sources with varying levels of success and failure. But what you're seeing here is a heated tool with a high intensity heat source from the head. And so doing a complex layup that, with the goal being that you get in situ consolidation and at the end of layup. And there's a lot of people working on this sort of material processing, and it's definitely something that we've picked up as an expertise.
So let me ask you a question, and I don't know if you're allowed to say it. What is wrapped around the roller?
I believe that's a Kapton. I believe that's a Kapton wrap. But yeah, so with the high intensity heat source and the higher part temps, what you're doing down at the roller interface changes. And there's Todd holding that actual test article. We made a handful of them.
All right, that's awesome.
Yeah, so that popped out of the mold. So the typical one of the typical problems with these, I'll call it a skin layup with thermoplastics, like a thin shell part that isn't a closed section, is they'll potato chip real bad. So if you try to make a flat panel with in situ consolidation with the thermoplastic system, you'll lay it up flat and it'll turn into a Pringle. And so having something that comes out of the same shape that you laid it up is the kind of the panacea of that process technology.
All right, this is awesome. So we don't have slides anymore. Is there a couple of videos we want to talk about?
So there's a couple more videos. So in that process development, we'll see what Matt cues up here. 3-ring circus. So this is ultrasonic cutting. So this is another technology that we've actually delivered a lot of, both into production and R&D environments. So that's an ultrasonic knife. That happens to be on the end of a robot. We've delivered them with our big machines and our robots. And it's not a new technology. Putting it on the end of a 6 or 7 axis machine is somewhat novel, as in there's not that many suppliers for that technology. And then the tricks for that process are, again, getting the highest throughput for cutting thick stacks, and then also doing part beveling, which is what you're seeing right now on that video. So do low angle bevel cuts with tool point accuracy and good edge finish. And I think you'll see a shot of the finished product here in a second.
I have a little confession to make. One time, a couple of years on Christmas, I used I used the ultrasonic knife to make Christmas artifacts from composites. So
okay, I thought you were going to tell me you carved your turkey with it.
Hey, you're giving me ideas in here. All right, this has been nothing short of awesome. Is there any more videos we want to play, or should we have some concluding words? So I see there's a video. Let's go ahead.
Real quick, yeah. Go ahead and rewind that. Yeah. Okay, so this is just a kind of a wide-ranging video. It just shows different pieces of equipment we've delivered throughout the years. This is for section 41. This is a twin-aisle airplane. Another twin-aisle. This is the A350 machine here. So we're doing fuselage sections in both those two. This is 777X. This is the demo machine that I'm sitting in right here. That part happens to be basically 10 meters by 10 meters. So it's a machine that's laying up at 4,000 inches per minute that you see there. So that's how it covers, basically, 12 meters so fast. Very same machine doing flat charge stringers here. Again, all the motion is at 3,000 inches per minute. I hate to say it, but we would never do that bi-directional again. We discovered that there's a critical length to a course, and that critical length happens to be 55 inches for this machine. If the course is shorter than 55, we should do it unidirectional. If it's longer than 55 inches, we should do it bidirectional. So if you see on the Blackbird later on, you'll see we do lots of unidirectional motion, and then when the courses get longer, then we'll go into bidirectional. So it shows the flexibility of our system in a way, I think. This is an actual 777X wing spar that we had to build here for Boeing to get our equipment approved. We still have the tool, which is really cool. They let us keep it, and we do demonstrations with it every now and then. That's
awesome. That's a cool giveaway.
Yeah, I know. It's nice to have. We have it right here. So if anybody wants to see how to build the spar, we'll throw it in and show them. But you can see here, this is I think a unique spar in that it's a in situ one-piece spar. The whole thing 110 feet long. So there's no splicing of pieces together. It's just one homogeneous part.
That's awesome.
This is an example of our what we call it's for some sort of engine part, engine nacelle or whatever. This is at GE, or used to be GE in Middle Rivers. And you can see it's quite a flexible system. There was actually 2 machines there. There's 4 x-axes. There's 3 heads shared between 2 machines. So we do complicated installations if that is what the customer needs.
That's awesome. This is a fascinating world, and I'm very happy to hear that the concepts of advanced manufacturing and what we talk about Industry 4.0 is making it to the AFP world. I actually often say something like when I'm in my class and talking to my students, I say an AFP machine is just a machine. It's just like it has no brain. Even if it's huge and big, what you put into there, there's almost very minimal closed loop control of knowing what is it that is happening. Like you set up a temperature and you hope that this is what it is. I'm glad that we've come a long way, and what you're showing in here is actually some closed loop processes, and this is nothing short of fascinating. So before I let you go, is there any option that you can, like Kyle or Todd, take us a little bit up close to the machine or something, or is the setup is very hard to do that?
Let me check with my media guy. Film me while I go to the head. Okay, we can do it, but I won't have headset. So.
All right, no problem. So before you do that, Todd, how about you give us some closing words from your side?
Yeah, so just to back up what you said, Industry 4.0 has been on the forefront of our mind for actually about 4 or 5 years now, closing the loop and getting reports out so that AFP becomes much more like a machining process where it's start the system, let it run till it's done, and then when you've expended all of your material, get a new head and go back out there with a lot of assurance that you're going to get all the way through the part. And with minimizing the hand touch and also collecting, huge amounts of data that you didn't used to have. So we can now analyze plies by statistics as opposed to goalposts, and it's very enabling. We went through one round with Boeing on it, and the next round we're very prepared for this hands-off approach, and we're really excited for the next customer to come along or this program. I know we're in a little bit of a slow spot here, but we're looking to space and military, and wherever the work's at, the next guy is going to get a really great setup.
Yeah, I totally agree with you. And even if there's going to be a little bit of downtime, what's happening in the world, I mean, it's definitely going to influence. I was talking to my team this morning, and I'm like, all right, we have to be a little bit innovative. But I believe that one aspect, which is human exploration of space, will never cease. And I personally do not foresee any way to do that without composites. So I think we're there for the long run. All right. So before I move on to Kyle to wrap it up, what about, how about you show us a little bit the machine behind you? And Todd, I cannot thank you enough for tuning in.
Yeah, we'll do it again for sure, and maybe we'll disclose more as we develop more. We're trying to be a little bit careful here with what we say, but trying to get the knowledge.
I was looking forward to visiting you guys next week because it was supposed to be Sampi next week, and I was Sampi is the biggest show in our community, and I was like, you know what, we're going there. We're definitely gonna drop by and say hi to EI, but Sampi is canceled, and the most important thing is everyone is safe right now. All right, thank you so much, Todd.
Okay, thank you. Yeah, we're sorry you can't come, but you'll be here in the summer.
All right. Yeah, hopefully. And I will still be with you on your camera for a minute.
Okay.
If you want to show us the machine, and I'm gonna maximize the screen on your camera for a couple of for a little bit of time. So go ahead, show us the machine from your side.
Sounds good. Here we go. Show them the enormity of the cell.
Okay, this is awesome. So we see in the background, Kyle, we see the Blackbird part that was manufactured.
Yep. He's got one of the Blackbird panels there, and we're very proud of those. We do those with an in-house oven cure. And so we've got like half a dozen of those kicking around, built out of different materials and built at different times. And we continue to build them to hone the tools and the processes that we're putting together that make up that AFP 4.0. It's a lot of, as you'd expect, it's a lot of technology pieces. hardware, software, process design, and so there's a Blackbird in process. So to get all of those pieces to come together requires a lot of iteration and practice. So there he's showing the robotic tool changer on the back of an end effector. So that's how we do the modular head change. There's an ATL head and a head stand. Again, all modular, robotic tool change. So we can quickly go from the AFP head that's on that machine right now to the ATL, to ultrasonic cutting, to wider formats.
This is nothing short of awesome. All right, I'm going to move to you, Kyle, for some closing words.
Okay.
So let's see here. So thank you for being a friend, and thank you for coming up on this LinkedIn show. And what else? What would you like to conclude with?
Well, definitely. I appreciate our friendship as well. It's been nothing but good. We appreciate the opportunity to be on here. We think this content that you're creating has a lot of value, and it's great that you're using the tools available and using the time available in this current work from home situation. You're taking full advantage, and we appreciate being part of it. So super excited to help you with that and to get a chance to be on here.
Thank you so much, Kyle.
You mentioned the visit. Anytime that, as the world starts to ramp back up, you're welcome out here anytime.
I am looking forward to start leaving the house, but in the meantime, we stay safe. We keep on doing what we can do to spread the good word of composites, and I cannot thank you enough for this amazing, nothing short of amazing demonstration and presentation. All right, I'm gonna let you go. Thank you so much. Have a great rest of the day, and talk to you again hopefully soon.
Okay, very good. We'll see you later, Rami.
Thank you so much, Kyle. All right, so thank you so much, everyone, for tuning in. This was a very special live from Electro Impact from Washington State. It's a privilege for me to be in this community and to have access to such good folks that are capable of, just sharing the knowledge and spreading the good word of composite. Tomorrow, we're going to have another special session. And I'm looking forward. We still have 2 days and we wrap up with our month. So thank you so much for tuning in, and talk to you tomorrow.